Hello folks, welcome back to my YouTube channel. This is the Vash, and in this video we will be talking about backward propagation. Okay, so before that, before understanding what is backward propagation, it is very important to understand what is forward propagation. So if you are new to my channel, then and if you have not learned about what is forward propagation, then you can definitely check out my previous video where I talked about what is forward propagation. Okay, where we learned about what is forward propagation. So in this video we will be basically understanding what is backward propagation. Okay. So as in our previous video we took this example of like whether based on the IQ and CGPA of a student, we were creating a model that would basically predict if the student will get placed or not, right? So basically taking the same example, let's say I won't be covering about backward propagation. Okay, let me revise it for some if you are new. So basically these my IQ and CGPA, these are my input features. Okay, this is basically my you can say input layer, and over here this N is my hidden layer, single hidden layer, having only one neuron. For understanding purposes I am taking only one neuron. Okay, and this is basically my output. Okay, output layer. Okay, yeah, so output layer will have only one neuron. Okay, so input layer will have a number of neurons based on your number of input features, which in our case we have only two input features, which is our IQ and CGPA, and place data is our output feature, and this x0 is our bias term. Okay, so basically let me again write the equation how we find out this y cap. So y cap is nothing but we basically pass the summation of this IQ into W1 plus CGPA into W2 with x0 in this activation function, right? We can write this as x0, which is our bias plus summation of these input features. Okay, I can write this as I equals to 1, 2, and this is general expression equals to 1 till like x of I into W of I. Okay, so this is a general expression for finding out this y. Okay, so this is backward propagation, like where we basically multiply CGPA, this input feature, with this with some weight, and add all and perform the same thing with this IQ into W1 and add these, right? And then we basically pass this to some activation function, and from here that particular output will again get multiplied with the W3, and again it will be passed to some activation function, and again it will go to this output, right? And then it will basically go to our output, which is y, which is our y. In forward propagation, what we do is we basically move from the input layer towards the output layer. Whereas in the backward propagation, what we will be doing is we will be moving from the output layer towards the input layer. Okay, and I'll be talking about what is the importance of this backward propagation, why we are doing so. Okay, suppose I'm naming this my placed column as y. Let me call it as y. Okay, y is basically my you can say true prediction. Okay, suppose my IQ and CGPA, I am passing it as 90 IQ. Okay, I am giving my model 90 as a value for my IQ, and CGPA as 9.2, and okay, and my model is giving y cap as, let's say, 0. Okay, I am getting y cap as 0. Whereas you can have a look, the value for y is 1. What does this mean? We are getting y cap equals to 0. This is basically our predicted output. Okay, this is known as our predicted output. Whereas this y is nothing but our, what is y? Y is nothing but our true output, right? We can say this as y is our true output. And if I talk about what is the loss, so you can say simply like loss equals to this predicted output. You can say y hat minus y. Okay, and I am squaring it. Why I am doing this square is basically suppose if my y hat is let's say, okay, in this case itself it will become negative, right? Because 0 minus 1 will be minus 1. So I want the value to be positive. Okay, so that's why like I am subtracting it. So this is my error, which my basically model is performing this error. So basically in forward propagation, what we do is we need forward propagation only because we want to basically reduce this error. Okay, our model is basically committing this error because it is giving us a predicted output as 0, and what our predicted output is 1. it is in generally you can say if my model is predicting y cap and the actual output is y, then the loss can be given as loss equals to y hat minus y whole square. This square is I am doing it because I want the positive value. So the backward propagation, the aim of this backward propagation is to reduce this error. Okay, aim of backward propagation is to reduce this error. Okay, so basically for doing this, for reducing the basically this error, this loss, this is known as the loss function. For reducing this loss function, we have something known as optimizers. Optimizers, optimizers. Okay, we have something known as optimizers for basically reducing our loss functions. The lower our loss value will be, the more accurate our model will be, right? Correct? The lower our loss value will be, the more accurate our model will be. So the use of optimizers, we are using optimizers only for the purpose of reducing our loss function. Okay, so there are many types of optimizers, like we'll be talking about them in upcoming videos. Like we have gradient descent, okay, optimizer. We have stochastic gradient descent, we have like mini batch stochastic gradient descent. Okay, mini batch stochastic gradient descent. We have Adam optimizer. Okay, Adam optimizer, and based on basically based on research, like this Adam, we mostly basically in practical applications we mostly use Adam. Okay, because basically these all of have basically it was like something. First we had gradient descent, then there was some flaws in gradient descent, then there came researchers introduced this stochastic gradient descent, and then again this stochastic gradient descent had some flaws, then there came mini stochastic gradient descent, and then came to solve some of the issues of this mini stochastic gradient descent, we have this Adam optimizer. Okay, mostly in our practicals we basically most of the cases we use this Adam optimizers. Okay, we'll be talking about in depth of these optimizers. Okay, cool. So yes, so we are basically using the optimizers to reduce our loss function. Okay, whereas in our case we have only one like we have only this, but where we can also have like many. Suppose we are only getting one error. Okay, so if we have basically more than one basic input feature, then we have something known as cost function. Okay, it's nothing, it's similar to like this. It's like cost function, we can say C equals to it's something like summation of I equals to 1 to m, and this would be like yn of subscript of I minus y subscript of I whole square. Okay, it's something like this. So we'll be talking about basically this loss function, how we can reduce this, and now we'll be talking about what is gradient descent. Okay, in upcoming video I'll be talking about gradient descent optimizer. So in this video, let's see how basically the backward propagation happens, how basically we reduce this loss function. So to reduce this loss function, we basically tends to do is we basically update these weights. You can have a look. We have these weights W1, W2 and W3. Okay, what we did earlier in the forward propagation, we multiplied these weights with our input features and passed it to our activation function. So in the backward propagation, moving from our basically input layer moving from our output layer towards our input layer, we'll be basically updating our weights. Okay, we'll be updating our weights. So we basically update these weights in as such our loss function gets reduced. Okay, this is going to perform like iteratively epochs. Okay, until and unless my loss function comes out to be minimum. Okay, suppose for the first time it will okay, let's take one cycle. So basically a forward propagation happens and we get y cap and our output is y. So our loss comes out to be y cap minus y whole square. Okay, now we'll be using optimizer to reduce this. So through for backward propagation, what we are going to do is we are going to basically update our weights. This W3, W2 and W1 will get updated. Okay, after updating this, let's say our loss gets a bit of reduced from earlier. Okay, and then again the forward propagation will take place and we'll get the loss for updated values of W, and then again we have some loss, so again the weights will get updated, okay, and again the forward propagation will happen at that particular updated weight. So epochs, this will happen in epochs, okay. When we'll be implementing these, we'll be passing the value for epochs, like how many epochs you want, okay. So we'll also be seeing this in a practical, okay. So this is theory. Theory is also very important, okay. So this is my loss function. So basically, to minimize this my loss function, we use backward propagation, okay. Okay, let me run this. Okay, so I'm rubbing these optimizers. I'll be talking about in depth of all these types of optimizers. What are their flaws? What they have improved in the next optimizer, and so. Okay, so this is my this is basically how backward propagation happens. So let's go a deep dive into this. So suppose we have this y cap, and our true output is y and our predicted output is y hat. So basically we can say our loss function is y hat minus y whole square, okay. This is my loss function, okay. So now let's see how our basically weight will get updated in the backward propagation. So in the forward propagation we have seen what happens, okay. In the backward propagation, what will happen? To reduce this loss function, we are using optimizers, and the optimizer will do is nothing. It will back propagate and update this W3 and back propagate and update this W1 from there, and this W2 will also get updated, okay, to reduce our loss function. Now let's see how basically our these W3, W1 and W2 will get updated. So I am generally writing this as like if this is my old weight, okay. Old weight is equals to, this will basically get updated with, this is basically a symbol of basically how we represent to update it, okay. I'm saying update this old weight with W, actually not it will not be like this, of course we are updating this. So W new will be such that update W old, okay, W old minus this is something known as learning rate. I am talking about this, minus learning rate into derivative of loss function divided by derivative of this particular W old, okay. Okay, I'll be talking about in depth about what is this. So this is something how our new weight gets calculated, okay. So yes, so over here, and this is basically my learning rate, okay. This value is given as small as possible. Something we basically starts to give it with like 0.001. It's basically you can experiment with this. You can give some value like 0.01 and check if your model works well. And basically the researchers have found like the smaller the value of this, not too much small, but like a decent number, like somewhere around 0.01 work. Seems to work quite well, okay, according to researchers, okay. And so yeah, over here del of L by del of old, I'll be talking about this, okay. Let's talk about this. What is this? So I hope you understood this how a new weight is getting updated. New weight is nothing but it's getting updated with the old weight minus learning rate is into derivative of loss function with respect to derivative of with respect to basically our old weight, okay. So let's talk about what is this del L by okay, del L by del L. Okay, so this del L by del of old is nothing as from the mathematics we know. Derivative is nothing but it is a slope, okay. It is a slope, okay. Derivative is nothing but a slope. So it is basically a slope. So we have to basically, I can rub this, okay, to make you understand. So suppose I have this okay, this is something like okay. Suppose my point is basically something like what I want to do is I want to come to the global minima. Okay, what I mean by global minima is basically I want to reduce my loss function. Okay, so I want to come over to this point. Okay, so suppose by finding out the slope of slope at this particular point, how can we find out the slope at this particular point? Like for that, like you can simply draw a line over here. Okay, a straight line. If the right side of this line is pointing downwards, that means the slope over here is negative. Right side is up. If the right side of the line is down, that means the negative slope. Okay, if the slope is negative, what we need to do is we need to add the weight. Okay, we need to increase the weight. We can say increase weight. Okay, because like suppose to come to this basically to come to this global minima, we need to of course like increase. Okay, we need to increase our values. Okay, and if similarly if we have loss function comes out over here, like if we draw a straight line, we can see our right side of the line points upwards, which means basically our slope over here is positive. If the slope is like positive, then if the slope is positive, then we need to reduce the value to come to this global minima. Okay, so this is something del L by del of W old. Okay, this to basically to minimize our global basically to come to our global minima. Okay, yes. So we'll be talking about this much more in upcoming videos, where I'll be talking about gradient descent, basically which is an optimizer for reducing our loss function. Okay, pretty much this only in this video, and I hope you like this video. If you like this video, please give a thumbs up and subscribe to my channel. Thank you.